Today I would like to explain about the Raynold transport theorem. Okay, there are three concepts in RTT, which the first one is the system, and the second one is control volume, and the three is physical quantity. And the first one, a system, a collection of fluid particles moving through space. The system involves time, and the control volume, a phase or a region in space and through which fluid can flow. The control volume is typically used in engineering application for analysis and the physical quantity like mass, momentum, energy that we use to analyze. We go to the diagram. So this is the RTT diagram. It shows that they have a control volume at times and the system material volume system at time. So let me explain. The control volumes, the shaded region represent the control volume at time, the region remain phase in space. And the second one, the system material volume. At time, the system fluid particles coincides exactly with the control volume, which is the shaded region. At times, T plus the delta T, the system moves part of axis of control region 2, H is area, meanwhile the fluid enter the control volumes. And the sections, regions 1, regions 2, and A1 and A2. For the region 1, fluids that enter the control volume during T inflow, meanwhile the regions 2, the fluid exits the control volumes during the delta T, which is our outflow. And the N1 is the cross-sectional area is in outlet respectively. So this is the diagram. Okay, we move forwards to the equations. Okay, for the equation, we have to know that the B system is equals to the BCV, which is the CV is constant with times. B system is equals to BCV the minus B delta T and the B2, which is T plus delta T. We are substituting the physics equation from the second one by divide T and then it will be like this. Taking the limit, which is a T is a near to 0 using the definition of derivative, we will get the dB system over dt equals to dBCV dt minus B in plus B out. And since the B1 and B2, okay, which is we now have the B row V1 and a B2 B2 row V2 T plus delta T and a B dot in equals to B dot 1 equals to limit approach to 0 B1 T delta T over delta T. Okay, so where there's a crossing area for the equation 1 and 2 since that the time rate of change of property B of the system is equal to the time rate of change B of the control volume plus the net plus of the control volume by the crossing the control surface. The influx B dot in and outflux B dot out of the property B in the case are easy to determine since there is only one inlet and one outlet. The velocities are presumably normal to the surface actions 1 and 2. To the another ones. So this is a generate of equations. This equation is the product of the velocity vector of point of control surface and outer vector at this point, which is a v dot n equals to v dot n cos theta v cos theta. Where theta is the angle between velocity and the outer normal. For theta less than 90 degrees, cos theta greater than 0, thus v dot n will be greater than 0 for the outflow mass. And from the control volume, theta is greater than 90 degrees, which is cos theta will be less than 0, thus v dot n will be less than 0. Okay, we move forward then to the phase control volume, which is dB system equals to d theta equals to d over dt pb dv integrated by control system pbv and d. The alternate RTT feeds CV dB system over dt d over dt pb plus integrate pbv and d. So this is why I said that before, that the inflow and outflow by the by degrees, different of degrees. Okay, so this one, like, all right. So for the 443, so that all these equations, but I have to simplify to be become like this. 443 is explains about the VV absolute over minus V control system, which defines the relative velocity V as the difference between the absolute velocity V absolute and the velocity of the control volume V control system. This is useful when the control volume is moving and it allows us to analyze and flow relative moving control surface. And equation 444 RTT for a moving control volume. This the term explained is dB, the system is the option of physical property B, and the integrate area of B with the control volume. The integrate of control system is a net flux B across the control surface. VR is relative velocity of the fluid as if you define in equation 443 before. The norm and the N is the norm of the control surface indicating the direction. Okay, move to 445. 445, the equation is here. And then it explains about it's similar to 444, but the V absolute, the absolute velocity is used instead of the relative VR, because why the equation is analyzing the flow relative to a stationary difference. And the 446 is as mentioned about the four steady state conditions. The property B inside the control volume does not change with time, which is a d del over delta t equals to 0. Only the net product of P across the control volume is considered. And then we go to 447. 447 says that dB system over delta t equals to d over at integrate of control volume rho b dv plus total mass m dot vr average for each outlet minus the sum of m dot r b average for each inlet. In this application, we measure rewrite 447 in terms of volume. In case, in such cases, we make the approximation m dot r equals to rho v, which is rho average v r average times a. This approximation is that when fluid density p is uniform over a. And then we have to approximate RTT for well-defined inlets and outlets. dB system equals to dt equals to d over dt of say control volume rho b dv plus sum up rho average b average vr average a minus sum of rho average b average v average a. Equation 445 becomes nominal when the property B contains a velocity When applying RTT to the momentum equation V equals to vector V, the approximation of equation 4 for it leads to error. Actually, we can limit error by including the correction factor when we discussed in chapter 5 and chapter 6. 447 to 8 apply of moving control volumes, but as discussed, the relative velocity must be for cases of is control. The mass flow M is relative to moving control surface since it's R subscript. So that's all from me. Thank you.